Okay, welcome back. So, in our last class, if you recall, I think we started the function of two variables and then limit of a function of two variables. Okay. So today we are going to discuss continuity. Continuity of a function of two variables. Of a function of two variables. Okay. So I'll explain the things, and after that I will run through this slide so that everything is perfect there. Okay. So as before, let us consider a function of two variables from some domain D in R2 to the set of real numbers. Okay. So then what we do, we say that the function f is continuous. F is continuous at a point your AB belonging to T if your given epsilon greater than 0, however small, there exists a positive number delta, your such that T stands your f of xy minus f of AB, it's less than epsilon, your whenever in 0 is x minus a whole square plus 1 minus 2 whole square is less than delta. Okay, and in fact, yes.
Will there be a 0 over there?
Where?
In the whenever statement.
Whenever statement.
0 is there in the limit. Not in continuity.
Even that is fine. Even when we were considering, this concept for limit, even then, because I'm always taking the positive square root of this, it was always going to be greater than 0. Okay, fine.
If x equal to a, y equal to b, then
a
at the point AB.
At the point AB, okay, just a minute. You are talking about, at the point AB itself. Yes, I think you have a point because, yeah, fine. I'm happy that you have closed it up because everybody, if you consider the limit, whenever we consider limit at a point, say A comma B, then in the domain, we may not include that point. AB because we are not worried about what is happening at the point AB, but we are worried about what is happening around AB, right? But here, I'll come back to this definition again. So basically, for continuity, what you must have, your limit xy, limit of f of xy as xy tends to AB, it must be equal to f of AB. Okay, so rather than starting from here, which is a bit difficult, let us start with this definition. Okay, we say that a function f is continuous at the point AB, where AB belongs to the domain of definition of the function g, right? Then we say that the function is continuous at AB if this happens. Okay. Now, if this is to happen, so then I can frame the definition. As this. Okay, fine. And again, here, earlier what we did, earlier in limit, I put this strictly, this 0 less than equal to this less than equal to delta. But here the thing is that because we are going to include this point, so then this part, it may become 0 as well. Okay, fine. So now let us consider a couple of examples here. Let us consider a couple of examples here, and then see what we can do about this continuity. Okay. So now let me just get back to this. Okay. Say, suppose we want to prove the continuity of a function at a point. I will take a very easy example. Okay. Say, suppose I am considering this function. This function is f of x squared, and I want to consider its continuity at the point 0, 0. At the point 0, 0. Okay, fine. So now I'll come back to this. Now let us look at this statement. Okay. If we look at this statement, then firstly you have to look at the left-hand side. The very first thing is that in order for the function to be continuous at a point, firstly the limit has to be defined. At that point. Okay, that is the first thing. The limit may exist. This limit on the left hand side, it may exist or it may not exist. Okay, fine. So now, if it doesn't exist, we are not going to proceed further. We are not even going to talk about the continuity because the limit itself doesn't exist. Okay, if the limit exists, then we are going to evaluate it. Okay, and after that, we are going to evaluate the function at that particular point, and then we are going to equate. And if they are equal, then we say that the limit exists. Okay, so now here, and again, when we are going to equate, then firstly, again, when I am going to consider the existence of the function at that point, firstly, the function has to be defined at that point, isn't it? Right? We are going to look into all these things. Okay? Fine. So now, if you look at this, if I want to, check whether given function is continuous at the origin or not, you can definitely see that at the origin the function is not defined, isn't it? Right? So
Yes.
that is why the question of continuity doesn't arise at all. The function cannot be continuous at 0, 0. Okay. Now, next thing is that let us try to redefine the function now. Okay. Let us try to redefine the function in such a way that fine. F of x y equal to, it is your x squared minus y squared divided by x squared plus y squared if x y is say not equal to 0, 0. Okay, and this is equal to 0 at the origin. Okay, so now we have reconstructed the function. Okay, and we have reconstructed the function in such a way that at the origin its value is 0. So that means whatever we had earlier here, so that has been eliminated. Okay, so that means your f of 0, 0 equal to 0. Okay, fine. So at least the value of the function at that particular point a, b, it exists. Okay, so now let me again come back to this. So now it all boils down to finding out the limit of the function. Is at the point 0. Okay, fine. So now we have already proved that this limit doesn't exist. Is it okay? Fine. We have already proved in our last class that this limit doesn't exist, right? So since this limit doesn't exist, even though the value of the function exists at the point 0, 0, right? So the conclusion is the function is not continuous at the origin. Okay, fine. So, however, now again, whatever we have done earlier, let us again reconstruct something. Okay, fine. Let us again reconstruct something. So, we have already seen that, I mean, this function, for this function, the limit exists. We have already proved that the limit is equal to 0. Fine? Okay. So now, if I now construct a function as this, so this is equal to 3x squared y, x squared plus y squared, when x, y is not equal to 0, 0, and this is equal to 0. Okay. If I define my function like this, then obviously you know that what is going to happen. So this is going to be f at 0, 0, right? So the definition of continuity is satisfied here. Okay. So in this case, we will say that the given function is continuous at origin. Okay. And you can easily check. That whenever we take polynomials, of any degree, they are always going to be continuous at all points. At all points in R2. Okay, fine. I mean, from single variable calculus, thank you. Single variable calculus, you have already learned that. Okay, so now let me come to rational functions like this. Okay, and you know that if I consider this function, say, so it is nothing but what? It is ratio of polynomials. It is nothing but ratio of polynomials, isn't it? Fine. So can I say that it is always going to be continuous at all points? I still haven't talked about all points belonging where? Yes?
All points in the domain of definition.
Exactly. At all points in the domain of definition. Okay. Always remember, whenever we take a rational function, which is nothing but the quotient or ratio of polynomials, it is always going to be continuous at all points in its domain of definition. Okay. So now, why I have brought this in? In the earlier example, I mean, see this particular example, right? The limit didn't exist. Didn't exist at origin, isn't it? Limit didn't exist at the origin. But the function itself is not defined at the origin. Okay. So the domain of this function would have been your R2 minus the point 0, 0. Isn't it? This should have been my domain. Now, if I take a point other than the point 0, 0, this function is always going to be continuous at that point. Okay, fine. Just a minute here. I'd like to mention. And another thing. Here, I was talking about the function. I'm talking about the continuity of the function at a particular point, right? So now, if we consider, I mean, a domain D. If I consider a domain D and of the function, and if the function is continuous at all the points in that domain, we say that overall the function is continuous at D in D continuous. Okay, fine. So this is about continuity. I mean, we will have enough example in our tutorial, so we don't need to worry about it. Okay. So what I am going to do now, I am going to shift my attention to concept which we are going to learn now is called partial derivative. Okay, so I just like to run through a slide, and after that I will begin my discussion. Okay, fine. So let us come to this. Okay, so here, what I have done, I have taken a metallic bar. You see here, it is the picture. It is the picture of a metallic bar. Okay. So what is being done here? I'm interested in the temperature distribution at all the points here, all the points of that metallic bar. So what is being done here? Say you may what you can do, like say you can dip the metallic bar, like say in some ice cold water. Okay. So then what you do, you just take it out after a while. So then you know that at all points its temperature is going to be 0 because it was dipped in ice cold water. So you just take it out, and then what you do at the top, you impart some temperature, say 100 degrees Celsius. Okay. So now if I take a cross section like this, you can see from here the dotted lines. Okay. So if I take a cross section by taking the slice through a vertical plane here, so then the cross section is going to look like this. So what is happening here? At the top, the temperature is going to be 100, and at all the other side, the temperature is going to be 0 degrees Celsius. So now, what is going to happen? After a while, the temperature inside this plate, say now, earlier we had taken a metallic bar. Since we have taken a cross section of this, this has become a metallic plate. So inside this plate, the temperature is going to settle down. And let me convince you, let me tell you, is that the temperature distribution is going to look like this. Okay, so at the top, so you are going to have some isotherms. These are nothing but isotherms. So along this line, the temperature is going to be the way they have been shown here. Okay, fine. So now, see, whenever we were talking about simple variable calculus, so you know that the derivatives are nothing but the rate of change of something. Okay, so whenever you have considered a function of one variable, say function of the independent variable, function say f of an independent variable x, then what we do, we take some increment delta x, okay, and then we take some ratio delta f by delta x. So that means we are trying to find out the rate of change of f with respect to that single variable x. Okay, so we were dealing basically only with one direction. But now, what is happening out here? So this metallic plate, this is 100 degrees Celsius, this is 0, 0, 0, and then I'm going to have like my isotherms. Once this temperature settles down, it is going to look like this. See, at the very top, it is going to be 100, it is going to be something like 99, so this is going to be something like 91, this is 85, and so on. As we go along, this may be 2, this may be 5, 2 degrees Celsius, 5 degrees Celsius, and so on. Okay, but now, here, if I want to consider the rate of change, then where am I going to consider the rate of change? I have to have some direction, isn't it? So now here, I may have rate of change here along this direction. Okay, so if I go from y equal to 0, say suppose like say the height was like say 20 centimeter, and which is something like say maybe your 10 centimeters. Okay, so if we go along this height, so then definitely I will see the change of temperature here. Is it okay? Fine. On the other hand, on the other hand, here I may consider rate of change along this direction, isn't it? Here also, you are going to have some change in temperature from 0 here, and from here there will be something, here there will be something. So in both the directions we can consider rate of change. Now earlier what you have? You had only one direction in single variable calculus. In single variable calculus you had only one direction. But here for the time being I am considering two variable calculus here, although we are dealing with multivariable calculus. So what is happening out here? I have more than one direction. So along this, I can consider that there is some change along y direction, and along this horizontal line, I can say that there is some change along x direction. Okay? So if we concentrate only in those two directions, then you are going to come up with the concept of partial derivatives. Okay? So now, again, your curious minds, it is going to again ask me, I know, that like in two dimensions, whenever I am taking this plane, I may have infinite number of directions. It is not necessarily only along x-axis or y-axis. I can have any arbitrary direction like this, isn't it? So what is going to happen to that? Okay. So now let me tell you that the mathematicians are clever enough, and mathematics as a tool can be applied there also, which again we are going to learn later on. Okay, so for the time being, let us concentrate only on partial derivatives along x and y directions. After a while, so maybe after 4 or 5 classes, we are going to deal with the rate of change. Again, that is going to lead me to some kind of derivatives. Okay, rate of change along an arbitrary direction, and that is going to be called something like directional derivatives. Which we are going to deal later. Don't worry about it. Okay, fine. When there is a way, there is a way. So the mathematicians have already found a way. So what is partial derivative? Okay, fine. So now let us again consider a function f of two variables. F is a function of two variables, something like this. Okay, and again, let us consider its domain like this. Okay, and then let me consider a point. Let me consider a point A. Let me consider a point AB. Okay, so now suppose if I consider this function f of xy, say at the point A. So now I may consider this function in such a way that I am going to keep your b fixed, but I am going to keep x variables. So then this is going to define some function like say g1x. I can define a function like this. Okay, fine. So now if I want to consider the derivative of this function, g1 at the point A with respect to x. So then what this is going to be, g1 prime A, this is simply going to be limit h tends to 0, your g1, your what? A plus h minus g1a divided by h. Is it okay? Fine. So now if I convert now g1 into a function of two variables now, what this is going to be, g1 was nothing but g1 was opting from the original function by keeping y fixed. Okay, so then this is simply going to be your f of a plus h b minus f of a b divided by h. Fine. Okay. So similarly, what I can do by considering variation only along one direction, we can define another function. Say g2y, I can define it to be f of ay, right? So then, if I consider the derivative of g2 with respect to ordinary derivative of g2 with respect to y at the point b, so this is going to be something like limit k tending to 0, your g2, your b plus k minus g2k divided by k, and eventually, if I convert it into a function of two variables, it is going to be limit k tends to 0, k f of a b plus k minus f of a. Fine? Okay. So basically, what we have done. So now, if I don't think about, yes.
It will be G2B. You have written G2K.
Oh, G2B. Sorry. Thank you. G2B. Yes. Yeah. G2B. Yeah. So now, what is happening here? Now, if I simply eliminate the role of these functions, again G1 and G2, what we have done, we have got two limits. In fact, limit h tends to 0, your f of a plus h b minus f of a b divided by h, and then I have got another limit k tends to 0, your f of a b plus k minus f of ab divided by k. Okay, fine. So now, okay, probably at least you have understood these in terms of ordinary derivatives, right? So let me simply erase this. Okay. What is happening here? This limit, in order to find this limit, what we have done, although we have considered a function of two variables, we have kept, one of those variables as constant, that is b, okay? And likewise, here what we have done, we have kept a constant, okay? So basically, although it is kind of ordinary derivative, because we have kept, one direction constant, but because we are considering a function of two variables, so that is why these are called, this is called partial derivative of the function f at the point ab with respect to x. Okay, so and that is denoted by fx ab. So this is the symbol for partial derivative. So similarly, this is the partial derivative of the function f at the point ab with respect to y, and this definition is this. Okay, so now if you want to make those, the point like say ab, that ab I have taken a fixed point. So if you want to consider it as a variable point, so like say I simply say that this. So this is simply limit h tends to 0, f of x plus h y minus f of x y divided by h, and then similarly this limit k tends to 0, your f of x y plus k minus f of x y divided by k. And these symbols are also used, del x and del f, del y, and also sometimes for the dx, this symbol. So of course, del f, del x at the point x, y. So these symbols are also dx, and similarly for this dy, these symbols are also used. Okay, so now if you have a look at this, so in the definition itself, so in order to find out the partial derivatives, what we did, simply we consider one of the variables as constants. Okay. So for example, suppose your f of x y equal to say x to the power 4 y cube plus say sin x y. I'm simply constructing it. Okay. So if I want to find out the partial derivative of this with respect to x, so then what I will do, I will consider y to be constant, and I will simply differentiate this with respect to x. So then what is going to happen? Y cube is constant, it will remain as it is. So this is simply 4x cube. Okay. So the derivative of sine is cos xy. Now again here y is considered as a constant, right? So the derivative of xy, then it is going to give me y, isn't it? Similarly, if I want to find out this, so then with respect to y, your x is constant, so x to the power 4 is going to be there. The derivative of y cube is 3y squared, and similarly here I am going to have. Is it okay? So this is the way we are going to proceed. So now let us come to a very important concept, the geometrical interpretation of the partial derivative, because that is going to be very, very important later on when you are going to learn tangent planes. Okay, fine. I will come to higher order derivative later on, but firstly let me finish this geometric interpretation. Okay, and after that, I'm going to do this function of more than 2 variables also. Okay, fine. So now, in suppose this is the domain of definition of the function f. Okay, so then you know that if I want to draw the graph of the function f of x y, so then what is going to happen? It is going to give me a surface. It is going to give me a surface here. Okay, fine. So and that this axis I am considering it. So now, suppose I consider a point AB here. This point is AB. This point is AB. Okay, fine. And then I'll try to find out the partial derivative of f with respect to x and then y at that point A. Okay, fine. So now let us see what is happening out here. So firstly, okay. So this is A. This is B. This is B. Okay, fine. So now, I mean, when trying to find out the partial derivative of the function f at the point AB with respect to x, what we do, we are going to fix B. So that means we are going to fix it, right? And you know that y equal to b, it represents a plane, right? So that plane is nothing but a vertical plane like this. That plane is nothing but a vertical plane like this, isn't it? Is it okay? Fine.
Yes.
So this plane is y equal to b. Okay, fine. So now let us see the scenario. So what is happening out here? Like your Okay. Suppose this is the point. Suppose this is the point A, B, C, where C equal to f of A. Okay, fine. So now, obviously, this plane is going to cut this surface on a curve, isn't it? It is going to cut out a curve C1. Is it okay?
Yes.
Fine. Okay. Now let us try to visualize that scenario. Because since my y is fixed, so what I can do, I can simply consider x z plane. I can simply consider x z plane, and this curve C1, it is going to be something like this. Okay, and this is the point. So this is x equal to a, and this is the point your AC, isn't it? Okay, fine. This is the point AC, right? So as before, what we did earlier, like when I had kept, y equal to b fixed, this f of, sorry. So I define this as g1x, isn't it? Right? I have defined it as g1x,
Yes.
right? So now you know that fx at AB, this is simply your dz dx at AB, isn't it? We have already seen that,
Sir,
right?
G1.
G1, yes, thank you, right? So that means, and this is nothing but the partial derivative of the function f at AB with respect to x, right? So now dz1 dx, what it does, what it tells you, it is nothing but the slope of the tangent, to the curve C1 at the point your AC. Is it okay? Fine.
Yes.
Right? So that means geometrically, what does the partial derivative at the point AB it signifies? It signifies the tangent line to the point A, comma B, comma C, where C equal to f of AB, right? At the point A, comma B, comma C on the surface, okay, and not on the surface. It is nothing but the slope of the tangent to the curve cut out by the plane y equal to b at the point A, B, C. So similarly, what you can do, you can consider then if you consider another plane, passing through AB, So I mean this, if you consider x equal to a, so then I mean you are going to get what? You are going to get another plane like this, and then another plane like this, right? And that is going to cut it at some curve C2, isn't it? So you are going to have a scenario. Like C2, and this is going to be the point your BC, and then again, I mean, what is going to happen? You are going to have a tangent line, right, to the curve C2 at that particular point, and which is going to signify the partial derivative of f with respect to y at that point. Is it okay? So I'm going to show you this thing in slides, so it is going to be more clear to you. Okay, fine. So this I have already defined. This I have already defined. What is partial derivative? Okay, fine. And then again your rule for finding partial derivative. So what you have to do, if you want to find a partial derivative with respect to x, you have to regard y as a constant, and simply you have to differentiate the function f of xy with respect to x. And to find fy, you have to simply regard x as a constant and differentiate f of xy with respect to y. Okay. So these are the examples you can try at home. These are the examples you can try at home. So, and definitely in our tutorial, we are going to do a lot of examples. So now, see, this is the scenario. This is the scenario. See, what we do when we try to find the partial derivative of f with respect to x. So then we are going to keep y as fixed. Say, suppose at that point in a, b, what we are doing, we are considering a plane y equal to b. So then it is going to cut the graph of the function, which is the surface, j equal to f of xy. It is going to cut it like this. Okay, right? So then, see, it is going to cut the surface into a curve, here. This is the red curve. Okay, this red curve. Okay. So now, if you take the cross section, so this is going to be your scenario. This is going to be your scenario, right? So along x-axis, you can see that this point is a0, and this is z-axis, and then this is the curve. This is the curve, right? Then you can see that this is the point AC, and here I have this tangent line, and the partial derivative of the function f with respect to x, it is nothing but the slope of the tangent line to the curve cut out by the plane y equal to b at this point. Okay, so you can see, you may consider this to be this increment to delta x, this increment to be delta j. Okay, fine. And then you will see an example after this. You will see an example after this. So what it has done, it is considering a function j equal to 5xy for this. As I have told you, whenever you have something like e to the power minus x ax square minus by square, something like that, you are always going to have a surface like mountain. Okay, fine. So I'll show you this surface. So what it is doing, this figure I am going to show you in a while. It is what it is trying to do, like, say, if I see this is the mountain which comes out as the graph of the function defined by this. Okay, so here what you can do, what is going to be your rate of change of height if you move along x direction, and if you move along y direction. Okay, so that is what the exercise is all about. Once I upload these slides, you please check it at home. Okay, I'm just going to show you the different scenarios. Okay, so along x direction, you will see that the angle of climb, the elevation, it is different. Okay, and along y direction, it is kind of steeper. Okay, so like obviously, in order not to get tired, I think in order to reach the peak, you are going to choose the x direction, isn't it? Fine. So now, as I told you that so far we have considered only a function of two variables, but we can consider a function of more than two variables also. So if I consider a function of three variables, so then partial derivative of f with respect to x, see, it is simply going to be what you are going to do. Now you are going to keep both except x, all the other variables constant. So it is going to be defined like this. Okay. So now, if you consider a function of n variables, and for this function of n variables x1, x2 up to xn, if you consider the partial derivative of this function with respect to xi, so what you have to do, you have to fix all the other independent variables, but for the independent variable xi, you are going to consider an increment and you are going to define the partial derivative like this. Okay, fine. So this is about function of more than two variables, and this can be written in terms of, I mean, vector notation also. I'll just explain it in Blackboard. Okay, and then again, say we can consider higher order derivatives as well. Okay, so let me get back to Blackboard. So I'll explain this to you. Okay, see, when I consider a function of more than two variables, okay, I may consider a point. I may consider, okay, suppose I'm considering this point. Suppose I'm considering this point. Okay, so now this is a point in n-dimensional space. Okay, so now if I want to consider the position vector of this point, what I can do, I can simply write it like this. I can simply write it like this. Is it okay? Fine. Say this is going to have, say, what? This IS location. It is going to be something like this. Okay, fine. So now, if I want some increment only at the IS location, so what I can do, like, say, I can define the unit vectors along x1, x2 up to xn direction as e1, e2 up to en, right? And this is nothing but 1, 0, 0, 0. This is going to be 0, 1, 0, 0, so on. Okay? And this is going to be 0, 0, this 1. As we had defined unit vector earlier, rjk was simply along xyz direction respectively. So since now I have, more than 3 directions, so that is why I'm doing it like this. Okay? So then what is going to happen? If you want to introduce, here an increment is, what I can do, if I simply write x plus h ei cap, so that is going to give me what? x1, x2, xi minus 1, but here I am going to have isn't it? Right? Okay, fine.
Yes.
So that is why you can see here. That is why you can see here. See, I can write the derivative of the function f with respect to xi, that is partial derivative. I can simply write it as this. See, this x is in boldface, huh? So this f of a function of n variables, I can simply write that in terms of a vector x bar. Huh? So this is x. So that is why they are doing this. Okay, fine. So now let us come to higher order derivatives. higher order partial derivative. Okay. So this is simple. So basically, like say, suppose I'm considering, I'm again taking a very easy one. Say suppose f of x1, f to the power of 1. Give the same example. Say sin xy, sin xy. Okay. So now, if I find out fx, so this is going to be 4x cubed y cubed plus your y cos x. We have already found out. Now again, you can see that whatever has resulted, it is again function of two variables x and y, right? So I can again try to find out the partial derivative of this with respect to x or y. Okay. So now, if I want to find out partial derivative of this with respect to x, what I am going to do? This is going to be simply this. So what I have to do is I have to again here, considering y as constant, I have to differentiate it once more with respect to x. So that is going to give me what? 12 your x squared y cube, and then for cos I am going to have minus sin xy, and from here again another y is going to come, and along with this is going to be y squared sin x. Okay, fine. And I can find out partial derivative of this with respect to y as well. So now this is not written as this. In fact, this is directly written as this. We don't need to worry about this. I don't have to write it like this. Just to explain it, I'm doing this. Okay. So similarly, if I want to find out partial derivative of this with respect to y, so then I'm going to keep x constant. So this is going to give me what? I mean 12 x cubed y squared, and then again this is going to give me minus your sin xy, and derivative of xy with respect to y is x, so that is why I am going to have xy sin y. Okay, and this is written as fxy. Okay, fine. So now another thing is that, like say from here I can find fy also. We have already found out earlier y also. So like equals to what? 3x to the power 4 y squared plus x cos x1. Right? Now again, I can think about partial derivative of this function with respect to x. So if I go by this, so it is going to be f of xy. So this is f of fy with respect to x. So then you can see from here that this is going to be 12x, right? And then this is minus sin xy, and derivative of xy with respect to x is y. So this is going to be xy sin xy. Okay, so now here you have seen what is happening here, that you have found out that fxy is fyx, but you shouldn't think that that is always going to happen. I will come back to that, but before that, let me tell you one more thing. So likewise, I could have found out fyy, right? And again, I could have found out further derivative of this with respect to x or y. So I could have found out fyy, right? Fyx, and so on. Okay. So there is a theorem which is called Clairaut's theorem, which gives you the condition for the equality of these two derivatives. Okay. So that is what I'm simply going to show you. So basically, if those two derivatives are continuous, then their partial, they are going to be, these two partial derivatives are going to be equal. Okay, fine. So here you can see. Yeah. And another thing, I had simply written it as fxx. It is also written as this: del2f, del x2. Okay. Similarly, this mixed derivative, these are for mixed derivative. Whenever both x and y are involved in the derivatives, it is called a mixed derivative. So it is also written as del 2f del y del x. Okay. So similarly, this fyx is going to be written by del 2f del x del y. Okay. Fine. So fyy it is del 2f del y2. Okay. So once you get used to it, the notation shouldn't be a problem at all. Okay. So now this is what Taylor's theorem is. So suppose f is defined on a disk D that contains the point AB if the functions fxy and fyx are both continuous on D. So then this equality happens. Then fxy at AB is equal to fyx. Okay, so again, I mean, in our tutorials, we are going to do a lot of examples, so you don't need to worry about it. Now, but let me tell you is that sometimes, I mean, like just directly differentiating a function with respect to x or y partially, it may not give you a true picture, okay, or there may be still some information hidden behind it. Okay, for some particular cases, we may have to find out the partial derivative again from definition. Okay, so what I mean by that? What I mean by that is that, see, say, suppose you are given a function. Suppose you are given a function f of xy. Okay, so then if you find out partial derivative of f with respect to x, so this is simply limit h tends to 0, your f of x plus h y minus f of x y divided by h. Okay, so it may so happen that in order to find out, the partial, the mixed partial derivative, so this, as you know, this is nothing but this, right? So then we may sometimes do this to be limit a tending to 0, your fx xy plus a minus fx xy divided by k. That is what I meant by whatever my earlier statement. Okay, let's start right now. Okay, so next, what I'm going to do, I'm going to do tangent plans. Okay, so after that, I'm going to finish this class. Okay, let me do it directly. Okay. Say, suppose I am considering a function of two variables, and I am denoting it by j equal to f of x. I am going to consider the graph of that function as a surface. Okay, and suppose this is your surface. This is your surface. Okay, and suppose at a point here, which corresponds to, say, this is a b 0. And suppose this is maybe let me call it x naught y naught. Let me call it x naught y naught. Okay, so let this point be x naught y naught j. So that means your j naught is nothing but f of x naught y naught. Okay, so now suppose I consider a tangent plan to this surface at this point. So then it is going to be something like this. It is going to be something like this. Is it okay? Fine. So now what is happening here? If I know the direction ratios of the normal at that particular point. Say suppose they are simply given by A, B, C. The normal at the point x naught y naught till now. So then you know that the equation of the tangent plan is given by this. Right? Does it ring a bell? We have already done this, isn't it? In our previous classes, yeah, we have already done this. Okay. So now I can modify this as z minus z naught. So this is equal to what? Minus. Of course, c is not equal to 0. So maybe I can write it as your a x minus x naught plus b y minus y naught. Is it okay? Fine. So now let us see what is happening out here. Okay. And of course, your capital A is equal to minus A by C and capital B equal to minus B by C. That's okay. So as before, if I consider the plan your y equal to y naught. So then what is going to happen? This is going to cut a curve out of this surface, okay? And then on that, I mean at that point, I can have a tangent line. Right? And the partial derivative of the function with respect to x at that point is going to be the slope of the tangent. Right? Now, let us see what happens to this equation along the plane y equal to y naught. So that means this is going to reduce to z minus z naught equal to a into x minus x naught. Okay? And as before, what we have seen earlier, like if this is the curve C1, okay, and this is the point your x naught. This is the point your x naught, and this is the point x naught z naught. So then the partial derivative of f with respect to x at the point x naught y naught. So that is going to be nothing but the slope of the tangent to the curve at that point. Is it okay?
Yes.
Fine. So now, that means in this tangent, okay. So similarly, if I consider the plane x equal to x naught, if I consider the point x equal to x naught, so that is going to give me, and again, see, like what will be the equation of this line? Equation of this line is going to be your z minus z naught. This is fx. Isn't it? Right? So similarly, this one is xj plan, right? So similarly, I could have got a I could have got something like this line would have been z minus z naught equal to your fy y minus y naught, right? So that means if you want to find out the equation of a tangent plane, for equation of a tangent plane on a surface at a point x naught y naught, on a surface z equal to f of xy at the point x naught y naught, or you x naught y naught z naught, where z naught equal to f of x naught y naught. So what you will have to do? you have to simply find out the partial derivatives with respect to x and y, right? And then plug it in where? Plug it in this equation.
Of a tangent.
Yeah, so plug it in here. That's it. Okay. So if we, I'll just take one example, and after that I'll finish. So this is what the scenario is. This is what the scenario is, as I have told you. See what is being done here. So I am considering this point P, which is coordinate x0, y0, z0. As you know, if we consider planes y equal to y0 and x equal to x0, so they are going to cut the surface. They are going to cut out, I mean what, two curves from the surfaces, like C1 and C2, and I can consider the tangents to those curves at that particular point. You are going to have a situation like this. Fine. So this is the scenario which I have done. Okay, I think I was using capital letter. These capital and small letters will, I mean, I changed the way I taught you. So this is going to be my scenario. This is going to be my scenario, as I have already told you. Okay, so that means here this a, small a, is nothing but the partial derivative of f at the point x0, y0. Okay, so similarly here b is going to be partial derivative of f at the point x0, y0 with respect to 1. Okay, so that is why if f has continuous partial derivatives, an equation of the tangent line to the surface j equal to f of xy at the point p x0, y0, z0 is simply this j minus z0 equal to fx x0, y0 x minus x0 plus fy x0, y0 y minus y. Okay, so I'll do an exercise. This normal, I will come back later on. But firstly, let us try to do this exercise. After that, I'll come back to normal and I'll finish this. Okay, so basically what we have to do.
Cannot be seen.
No, that is fine. I'll come back to that. Don't worry. So here, basically what we have to find. So this is the surface j equal to 5 minus 2x minus y square. This one. Okay, and this is the point 1, 1, 2. So at this point, this is the tangent line. We have to find out the equation of this tangent. Okay, so now, from our earlier discussion, we found out that at the point P x0, y0, z0, okay, the equation of the tangent line is given by this fx x0, y0 x minus x0 plus fy x0, y0 y minus y. Okay, so now here fx is simply the partial derivative of this with respect to x. So fx is simply zx. So zx here it is going to be your minus 4x, and zy it is going to be minus 2y, right? And zx at the point your 1, 1. So it is going to be 4x. So it is eventually it is going to be minus 4, and this is going to be minus 2, right? So if I use this formula, so then this is going to imply me z minus z0. Z0 is 2. So this is equal to minus 4, x minus 1, minus 2, y minus 1, y minus 1. So whatever comes out of this, what is going to come out of this? If I take this 4x plus 2y, so this is going to be plus 4 plus 2, that is 6. 6, and of course z is already here. So 6 plus 6, and if you bring this 2 to the right hand side, it is going to be 8, right? Yeah. So this is my equation of the tensor. Okay. So now another interesting thing here. Okay, fine. So another interesting thing. See, forget about the partial derivative. When we consider the equation of the tangent to the surface at this point, the surface at this point. So then, what was happening? Your just a minute. Your the equation was given by x minus x naught, b y minus y naught plus c j minus z naught. This is equal to 0. Okay, fine. And now we have found out that the equation is given by something like this. If I convert so now if I convert this, I can convert it into something like this, isn't it?
Yes.
Okay.
Yes.
Fine. See here, what was ABC? They were nothing but the components of the normal, isn't it? Fine.
Yes.
So if you compare that to this equation, so what it becomes? You simply fx at x naught y naught, fy at x naught y naught, and this is minus. Is it okay? Fine.
Yes.
Right? So this is the way also you can interpret the normal vector. Okay? So this is going to give you the components of the normal vector. I'll come back to this again. I mean, in my next class, I'd like to tell you something more on that your outward normal and inward normal. Okay, so if I forget, please remind me in my next class. Okay, so with that note, maybe before that, see, this is what it is. And you will see that here something like minus n is written here. I'll come back to that in my next class. Okay, please remind me that. Okay. Fine. Just a minute. I'll just show you here itself. Here itself, you can see that, right? You have this normal plan given by, I had written n, here they are giving minus n. I'll tell you why they are doing it so, and you don't need to worry about it whether it is plus or minus. I'm going to give you a way, where you won't have any confusion between plus and minus. Okay? Right? So this I'm going to explain in my next class. Okay. So please remind me about that. So with that note, I'm going to finish this class. Thank you.